All right, so example 4 says an animal shelter has 160 feet of fencing to enclose 2 adjacent rectangular playpens for dogs. See the following figure. What dimension should be used to enclose the area? What dimension should be used so that the enclosed area will be maximum? So let's think about this. We need the area of, well, we have the total fencing. That's one of our 2 formulas. And then we also have the area. So let's look at this figure and see what it is. So here we have an X, and a Y. Let's go ahead and finish the picture. There's a couple extra X's and a couple extra Y's. So if I'm looking at the fencing, it looks like I have a total of 4 X's. So the fencing is going to be 4 sides that are X's, and I have 3 sides that are Y's. 4 X's and 3 Y's. And I know with the 4 X's and 3 Y's, that's my fencing. That has to be 160 feet of fencing. We'll come back to that in just a second. So now let's look at the area of this. So the area of this is the total width times the length. The total width of this would be X plus X, or 2X, times the width, which is Y. So the area is 2X and Y. We want to maximize the area, and we look at that area equation. It's in terms of 2 variables, so we can't maximize it as is. We need to use our other given information to figure it out. So let's look at the 4x plus 3y equals 160 equation for the total fencing. That's our restriction equation. I'm going to go ahead and solve for y by subtracting 4x from both sides. When I subtract 4x from both sides, I have 3y equals negative 4x plus 160. Now I'm going to divide each and every term by 3. When I do that, I get y equals negative 4/3 x plus 160 over 3. Neither of those fractions simplify. So what do I do now? I take this, now that I've solved for y, I can plug that back into the equation that I'm trying to maximize. Again, I'm trying to maximize this, but the only way to maximize it is if it's in terms of one variable. So this is going to be 2x times negative 4/3 x plus 160 over 3. Distributing, I have area equals, well, that'd be negative 8/3 x. Let's see what we would have. We would have plus 320/3 x. And sorry, this one should be an x squared. Negative 8/3 x squared plus 320 over 3x. That's my area equation in terms of one variable. That's what I want to maximize, so I need to find its derivative. Its derivative using the power rule, bringing the power down, would be negative 16/3 x plus, well, the derivative of 320 over 3x would be 320 over 3, 3/23. I'm going to set this equal to 0 to find its critical values. It's never undefined, so I don't need to worry about that. Subtract 320 divided by 3 from both sides. I have negative 16/3 x equals negative 320 over 3. Multiply both sides by the reciprocal, so I'm going to multiply both sides by negative 3/16. Negative 3/16. And I end up with x equals, I'm getting x equals 20 when I plug that into my calculator. Okay, so this is our derivative. We got our critical value. We need to make sure this critical value is a maximum or a minimum. Since the first derivative is nice, not too bad, I'm going to use the second derivative test rather than the sign chart. So the second derivative test here would be the derivative of negative 16/3 x is simply negative 16/3. The derivative of a constant is 0, so that tells me my second derivative is negative, no matter what x value I put in. Second derivative negative means my original function is concave down. If it's concave down and I'm at a critical value, that tells me that at x equals 20, I have a maximum, which is exactly what I wanted, is to maximize the area of this. So now I need to go back. Remember, x equals 20 is my critical value that gives me the maximum, but that is not the answer to the problem. Go back and reread the problem. It says what dimensions should be used. So the dimensions of the fence are the length times the width. The length of it is 2x. Well, if x is 20, that would tell me that it would be 20 times 2, which is 40 feet. And then the width of it is y. Remember, y is negative 4/3 x plus 160 over 3. So y would be negative 4/3 times 20 plus 160 over 3. plug that into your calculator, and you end up getting with y equals 80 over 3, and that's in terms of feet. So I'm going to go ahead and write that more realistically. You'd never say 80 feet, so I'm not going to write it as a mixed number. That's 26 and 2/3 feet. And even then, we could do 2/3 of a feet. 2/3 of a feet, if a foot is 12 inches, so 2/3 times 12 would be 8 inches. So it seems to me like I'm getting 40 feet by 26 feet and 8 inches. So each of the x's would be 40 feet, and each of the y's that you see in there, the length of the entire pin, the width of the entire pin would be 40 feet, and the length of the pin would be 26 feet, 8 inches. Each of the x's you see would be 20 feet, and the y's would be 26 feet and 8 inches. We did prove this as a maximum, so that problem is done. Right, on this next problem, let's take a look. It says a rectangle is bounded by the x-axis and the semicircle y equals the square root of 25 minus x squared. See the figure below. What length and width should the rectangle have so that we maximize its area? So that rectangle is inscribed inside of that semicircle. So first of all, let's analyze this xy thing going on here. If this is the point x, that means this length right here would be x. Notice this circle is centered at the point 0, 0, so it is symmetric about the y-axis. What I mean by that is, if this side is x right here, then we know this side right here is x as well, which tells me that the total length between these two things right here, this total length would be 2x. And then if I look with my y value right here, this is my y value of that point, so that's y, so it seems that the height of that rectangle would be y. So if I want to find the area of this rectangle, the area of this rectangle would be its width, which is 2x, times its height, which is y. Again, it says what length and width should I do to maximize its area, so I want to maximize the area. To maximize the area, I need this in terms of one variable. Right now it's in terms of two variables, but it's not as bad as I think because y is already given to us in the equation. Y is the square root of 25 minus x squared. So changing this area equation into one variable, I'd have a equals 2x times the square root of 25 minus x squared. Again, this is the area that I want to maximize. To find the maximum of this, I need to find its derivative. To find its derivative, I'm actually going to have to use the chain rule. So maybe it would help me looking at this as 2x times 25 minus x squared raised to the 1/2. And let's go ahead and find that derivative. Sorry, I said chain rule. There is a chain rule, but the primary rule that we're going to use is the product rule. First function being 2x, the second function being 25 minus x squared to the 1/2. So let's go ahead and find the derivative. It's the first, which is 2x, times the derivative of the second, which would be 1/2, times 25 minus x squared. Power minus 1 would be negative 1/2. Never forget the derivative of the inside. The derivative of 25 minus x squared is negative 2x. So that's first times the derivative of the second, plus the second, 25 minus x squared to the 1/2, times the derivative of the first. Well, the derivative of the 2x is simply 2. Let's go ahead and clean this up and see what we have. Seems like the 2's in the first one can simplify. So I'm going to throw that negative power into the denominator, make it into a square root. So it looks like I have a negative 2x times x, which would be negative 2x squared on this first one. And on bottom, it looks like I have a square root of 25 minus x squared. Then on the second one, it looks like I have, well, it's 2 times the square root of 25 minus x squared. So that's my derivative function right there. I'm going to want to simplify that. What I'm going to do is I'm going to get a common denominator on this one, so I can combine it into a single term. So I'll multiply the top and bottom times the square root of 25 minus x squared on both the top and bottom. If I did that, I would have a prime equals, well, I still have my minus 2x squared all over the square root of 25 minus x squared. Looks like I'd have plus 2 times, well, the square root of 25 minus x squared times the square root of 25 minus x squared is 25 minus x squared. I'll distribute that 2 momentarily. And then on the bottom, I have the square root of 25 minus x squared. I'm going to continue doing some simplification here. So I have negative 2x squared all over the square root of 25 minus x squared. Then I have plus 50 minus 2x squared all over the square root of 25 minus x squared. They have a common denominator, so I can add the numerators, keep the denominator the same, 25 minus x squared. So I have negative 2x squared plus negative 2x squared would be negative 4x squared, and then I'd have plus 50. All right. So that's my simplified version of, sorry, that was the derivative every single time. That's my simplified version of the derivative. Again, I need to find the critical values of this. So I need to find when is this equal to 0 and when is this undefined. So the derivative is equal to 0 when the numerator, negative 4x squared plus 50, is equal to 0. Subtract 50 from both sides, and I'd have negative 4x squared equals negative 50. Divide both sides by negative 4, and I'd have x squared equals, well, that'd be 50 over 4, which simplifies to what, 25 over 2. They have a 2 in common. So now I'm going to have x squared equals 25 over 2. I take the square root of both sides. Remember, there's plus and minus, but the negative doesn't make any sense here because x is in the first quadrant. It's the point, the ordered pair, xy. X is in the first quadrant and has to be positive. So this would be x equals, well, it would be the square root of 25 over the square root of 2. Putting that into my calculator, I'm going to end up with 5 root 2 over 2. So this is my critical value when the derivative is equal to 0. When would this be undefined? Well, it would be undefined when the bottom equals 0, so I'd have the square root of 25 minus x squared equals 0. Square both sides of this equation. I'd have 25 minus x squared equals 0. Add x squared to both sides. I'd have 25 equals x squared. Take the square root. Again, x has to be positive. We don't need to worry about the negative, so I'd have x equals 5. Let's think about x equals 5 real quick. If we go back to this picture and look at this, x equals 5, it looks like the radius of my circle is 5. So x being 5, we'd be on this point right here. I would have no area. So 5 is one of the solutions that we actually don't need to consider. We could have still done this and tested it, but we don't need to. All right. So we need to check this critical value of 5 root 2 over 2. We either need to do the first derivative test or the second derivative test to verify that this is actually positive. Well, just looking numerically at root 5 over 2, if you do a decimal approximation, it's about the number 3.53, 3.54 and change. So I'm just using that to get an idea. I need my number line, so I have my number line. I have my derivative that I'm plugging it into, a prime, and I have this number right here. Well, first of all, 0 is the lowest it can be. I have my critical value of 5 root 2 over 2, and then we already noted that the maximum is not inclusive but goes up to 5. So I need to pick some numbers to plug into the derivative. Again, the derivative being negative 4x squared plus 50 all over the square root of 25 minus x squared. I'm going to pick a number between 0 and 5 root 2 over 2. Again, 5 root 2 over 2 is about the number 3.5. So I'm going to pick about a 1. And then bigger than 5 root 2 over 2 between 5, how about the number 4? Plug in the number 1. 1 squared times negative 4 plus 50. Looks like I'm getting a positive number there. On the bottom, 25 minus 1 squared, square root of that looks like I'm getting a positive number, so I do have a positive. Let's try the number 4. If I try the number 4, 4 squared is 16 times 4 is negative 64, so I'd have a negative number on top. On bottom, 4 squared is 16, 25 minus 16 is 8, square root of that would be a positive number. Negative over a positive is a negative. So indeed, I do go from increasing to decreasing as desired, making this point with the first derivative test a maximum. So I have proven that 5 root 2 over 2 is a maximum, but let's go back to the problem and interpret what the heck they wanted. It said, what length and width should we have so that the area is maximum? Well, remember, the length of it was 2x, so that should be 2 times 5 root 2 over 2, which would simply be 5 root 2. That should be my length. And my width was y, and again, we know that y is the square root of 25 minus x squared, which was 5 root 2 over 2 squared. Go ahead and plug that into your calculator. I'm actually getting 5 root 2 over 2 for my y value as well. So it seems to me like what would we do for our dimensions of this? Well, we would make the length equal to 5 root 2, and we would make the width equal to 5 root 2 over 2. Doesn't have units, so this isn't inches or feet or anything like it, but there it is right there. I could have been a little more lenient and allowed decimal approximations on this one, but I went ahead and went exact on this solution.